welcome back. In this video, we will introduce the multiple linear regression model as an extension of basic linear regression. So we'll start by introducing the concept of confounding variables and talking about why a confounder could potentially be a problem for us in modeling. We'll then define the multiple regression model, talk about what that looks like, and then we'll talk about how to make predictions and interpret coefficients from this model. So let's start with an example. As you might know, statins are a class of drug widely used to lower cholesterol. Previous research has suggested that adults with elevated LDL cholesterol may be at increased risk for events like heart attack or stroke. So in 2013, the American College of Cardiology and the American Heart Association recommended that statin therapy be considered for individuals with cardiovascular disease, high LDL levels, and people with type 2 diabetes. Now, policy analysts have estimated that almost half of Americans age 40 to 75 and nearly all men over age 60 fall under these guidelines. So this is a very big section of the U.S. population. There is some concern, however, that increased use of statins may be associated with risk of cognitive decline. So we'll look at the data by considering a smaller subsample of the data from the PREVEN study. Our data set's called preven.samp. I do want to really emphasize here that we're using a smaller subsample of the data not for accuracy purposes, but for illustration purposes, so that we can more clearly see the individual points in the data. So we'll get this data from the OI Biostat library in R. Let's go ahead and start visualizing this. So here in this data set, statin equal 1 for statin users and statin equals 0 for non-statin users. So we have what's called a binary variable. What you're looking at here is a scatter plot of this data where the color of the point represents whether or not the individual is using statins. So the coralish points are the zeros, the non-statin users. The blue teal points are the statin users. A couple things to notice. There is a linear trend here, no matter what. As age is increasing, the RFFT score, or the rough figural fluency score, is decreasing. Again, remember that is a measure of cognitive efficiency, ability to multitask, things like that. So there is a decreasing trend. We are seeing more statin users in the higher age groups. The points are really clustered together though, so it's difficult to see whether or not the pattern is truly changing. This statin use might be an example of a confounder. We say that a confounder is an additional variable related to both the response and explanatory variables in a model. So there might be a relationship between statin use and age. Higher individuals are more likely to use statins. There might be a relationship between statin use and increased cognitive decline. So how do we handle this confounding? Well, we can extend our model. Let's add statin use into our regression model. We can do that by using multiple regression. So in general, we'll let y denote our numerical response. We'll let x1, x2, all the way up through potentially xp denote p potential explanatory variables in our model. So then we write our model as y1, or y, our response variable, is a function of some intercept term plus beta 1 times variable 1 plus beta 2 times variable 2, all the way up to beta p times variable p plus epsilon. So we're now just making our model a little bit longer, adding more variables to this linear regression model. So let's write the multiple regression model for predicting our FFT score based on age and statin use. So we would predict our figural fluency score with some intercept term beta 0 plus beta 1 times age plus beta 2 times statin use. So we've just added another term. That's it. We now have 3 regression coefficients in this model. We still have one intercept beta 0, but now instead of 1 slope coefficient, we have 2. In order to fit this extended model, we can simply use a plus sign to add additional terms. So our new model is a linear model that measures how our FFT changes or depends on age plus statin use. So that's how we'll read this. Our data set being the PREVENT sample data. Looking at our model, we have an intercept term, we have a coefficient or a slope on age, and a slope on statin use. So our fitted model is our FFT is 137.882 minus some effect of age, so age tends to decrease that. There is actually a positive effect of statin use. Statin use has a positive slope, so it looks like it's actually increasing this figural test score. For a statin user then, let's simplify our model just a little bit. Remember that statin users are coded in this data set as having a value of 1. So for a statin user, our predicted RFFT score is 137.882 minus 1.271 times age plus 0.8509 times 1. So notice our intercept has increased slightly. We combine these terms together. For a statin user, our predicted value is 138.7329 minus 1.271 times age. For a non-statin user, we'll plug in 0 for statin use. That term will drop out, and our predicted figural fluency score is 137.882 minus 1.271 times age. So what has changed now by introducing statins into the model isn't our slope on age. Statin use isn't affecting that. They're not related in terms of terms in the model. The intercept is just changing. Looking at the model summary, what can we see? Well, it looks like the intercept is quote, statistically significant. So in other words, it's strongly different from 0. Our age looks like it's non-zero as well, but take a look at the row for statin use. Statin use has a very high p-value, so it is possible that this added term related to statin use isn't really important. It's not really contributing much to our model. And in fact, if you look at the estimate for the slope coefficient for statins, it's much smaller than the standard error actually is. So let's make some predictions with this model. Subject 1 in this study is 55 years old and has an RFFT score of 62. This is also a subject who is not taking statins. So let's find their predicted value and see how well we did. So here is our model. We'll plug in 55 for age and we'll plug in 0 for statin use. Excuse me, this should be a does take statins, it looks like, because we're plugging in a 1, so apologies for that. Our predicted score is about 68. Their actual score was 62, so not too bad. Subject 2 doesn't take statins. We're going to plug in 0 here. Again, apologies for the typo. So subject 2, who did not take statins, we're predicting a value for 56. Takeaway point here, in a multiple linear regression model, we'll plug in values to make our predictions, just like we would in a simple linear regression model. Now let's talk a little bit about interpreting these regression coefficients. These are things that we really want to assess one at a time. Their effect is, in other words, isolated from the other variables. So for example, let's look at this age coefficient, which was negative 1.271. To interpret this, we could say the following. Holding statin use constant, so statin use isn't allowed to change. A 1-year increase in age would be associated with a decrease in the predicted RFFT score by 1.27 points. Let's look at statin use. Now we're holding age constant. Age isn't really changing here. A statin user is predicted to have a 0.8509 point higher RFFT score than a non-statin user. In the next video, we'll look at multiple regression a little bit more in depth. I'll see you then.